All right, so we're going to start talking about specific heat and calorimetry today. As we move into our thermochem unit of chemistry, you're going to see thermochem relates to, as thermo means the heat of an object. All right, heat comes from energy, and that energy can then be transferred into other surrounding objects and surrounding substances. So we're going to look at how that heat transfers and how it's contained in different objects. All right, so starting off, it's happened to you. You've gotten in the car on a hot summer day and went to buckle up, and ouch, the metal on the seatbelt burns you. However, when you go to pick up that water bottle because you're parched, it's hot outside, and you drink the water in the bottle, it's not nearly as hot as that seatbelt, right? It may be a little lukewarm, but it's not going to burn you. Why is that? Why does one burn you and one doesn't when they've both been sitting in the same car for probably the same amount of time in the same temperature outside? All right, it's because of the specific heat or the heat capacity of those objects. The heat capacity refers to the amount of energy that's required to raise just 1 gram of that substance by 1 degrees Celsius. All right, and so that's talking about the energy that we need. So we're going to measure it in joules. Again, note, we're only changing 1 gram of that substance. So these numbers are going to be pretty small, but when we look at water and liquid water, all right, it only takes 4.18 joules of energy to raise the temperature. You may look at that and go, oh, well, that's not too small, right? It's a pretty significant number, but you're talking about just 1 gram of water. Think about that water bottle and you were to put it on a scale, the mass is much greater than 1 gram. So it's going to take a lot of energy by the time you change the temperature of that entire bottle of water. All right, so when we look back at our seatbelt example, that's why that seatbelt gets a lot hotter a lot quicker than your water bottle. It takes a lot less energy to heat up the seatbelt by 1 degree Celsius than it does that water bottle. All right, so some heat capacities of different common substances, so you can kind of see a comparison. Liquid water here is 4.18. We just mentioned this one. All right, you're going to see that a lot. Solid water, which we know is ice, is 2.1. All right, so that's half the amount of energy is required to heat up ice as it is water. All right, so that's why you'll see ice melt so quick, and ice, as soon as you take it out of the freezer, has heated up and melted down. But water, it takes it a little while. If you have a cold glass of water, it's going to take it a second to turn to room temperature because their specific heats are different. All right, and then rubbing alcohol, aluminum, gold, and so look at how small the specific heat of different metals are. So this is why your metals are going to get so much hotter quicker because it takes less energy to heat those substances up. All right, so if we look at these, which ones are going to hold heat the best? Which one's going to be the most resistant to change? Out of what we have listed here, our water would hold it the best. All right, and what's going to hold it the worst? Whichever one that requires the least amount of energy to change, which would be gold. So that's why gold is easily melted down and formed, because all it takes is a little bit of heat to increase the temperature of that substance. All right, so we're going to take a quick second and watch this video on YouTube that talks about the heat that's contained within different objects. All right, so in understanding what the specific heat of a substance is, we can then determine how the temperature is going to change given a specific amount of energy that's transferred, and vice versa, determining how much energy is transferred based on a temperature change or the mass of the substance. So you have your specific heat equation, Q equals MC delta T. Q is our variable that's going to refer to quantity of heat or energy that is transferred. Remember, we measure that in joules. M, as usual, is going to be the mass. C is the variable that we use for specific heat, what we've just been referring to. All right, and then delta T, remember delta stands for change, and so delta T equals the change in temperature. Remember, that is always final minus initial, so the final temperature minus the initial temperature will tell you how much it changed. All right, so let's look at some example problems. Here's some common, before we get to those example problems, here's some common specific heats of different substances. If you just want to go back and look and to compare, as you're looking, look how small the specific heat for these metals are. Compared to that of water, again, we have our 4.18 for liquid water, and then again, you can see the difference here with steam and ice and how they change. All right, so moving on to example 1. What is the change in heat energy? So I'm looking for heat energy, which is Q, when 114.3 grams, there's my mass, of water at 14.5 degrees Celsius is raised to 17.9. So here's my temperature initial and my temperature final. Let's go ahead and plug these in and let's see what variables we have here. I have 114.3. And then I have a final 17.9 minus initial 14.5, which is going to give me a delta T of 3.4. So when I go and I plug this into my equation of Q equals MC delta T, I get Q is going to equal the product of 114.3 times 4.18 times 3.4. All right, all I did was plug those numbers in for their variables. All right, and that gives me a heat energy value of 1,624.4 joules of energy transferred as that water increases in temperature. All right, so all you're doing are plugging those value variables in and solving for your missing variable algebraically. Example 2. A sample of mercury is heated from 25.5 degrees Celsius to 52.5 degrees Celsius. That is our change in temperature. In the process, 3,050 joules of heat are absorbed. What mass of mercury was in the sample in order to absorb that amount of heat for that temperature change? All right, so let's look at what variables we have here. I have 30, 50 joules. I'm solving for my mass and my C value, which is specific heat. I know that because if I look back here at the table, my C stands for specific heat and mercury is 0.14. All right, so we've got our C value there. That'll always either be given to you or it's going to be what you are solving for. So in this case, it's given to you. And then a change in temperature with final 52.5 minus initial 25.5 to get a grand change in temperature of 27 degrees. All right, so now that I have my variables, I'm going to go and plug them into my equation. Q equals MC delta T. So my Q value equals 3,050. And then my M value is what I'm solving for. I have a C value of 0.14 and a change in temperature of 27. All right, when I simplify these two numbers together, I get 3.78. All right, so now let's rewrite this equation with that side of my equation simplified. And I'm solving for M. So I'm going to divide by 3.78, move everything to the left. 3.78, and I get a M value of 806.8 grams equals my M. All right, I'm going to circle that here because I know I kind of wrote it close to the other one. But I have a mass of 806.8 grams of mercury. Let's take a look at example 3. What is the specific heat of a metal if its mass is 26.86 grams and it requires 418.8 joules of heat to raise the temperature from 27.4 to 67.3. There's my change in temperature. All right, so my Q value given is 418.8. My mass is 26.86. my C value, remember I said it'd either be given or it's going to be what you're looking for. All right, and then my change in temperature is 67.3 minus my initial of 27.4, which gives me a change in temperature of 39.9 degrees Celsius. So now that I have my variables, we can go plug those in to my equation of Q equals MC delta T. So my Q value, 418.8 equals my mass, 26.86, C, and then delta T of 39.9. All right, so let's go ahead and simplify this right side of your equation. So when you multiply 26.86 with your 39.9, you are going to get 1071.714. All right, and that is set equal to your 418.8 for your Q value. So once we divide on both sides to solve for C, 1071.714, and same thing over here, 1071.714, those cancel out, and I find that my metal has a specific heat energy of 0.390 joules per grams Celsius. All right, so there's my final answer. That is the specific heat of that unknown metal. Right, so now moving into calorimetry, we can use these heat equations in order to measure how heat is transferred. All right, so when we look at calorimetry, the amount of energy lost is equal to the energy that's gained. So in calorimetry problems, what happens is we take a piece of metal, all right, and it is red hot. We find some red. It's like flaming hot. You put it in the fire, and now we're going to douse it in the water and cool it off. All right, so what's going to happen to the temperature of that metal? It's going to significantly drop, right? It's going to cool it off very quickly. It's going to happen to the cup of water. That water is going to warm up ever so slightly. And so the amount of heat that this piece of metal lost is what warmed the temperature of the water up. All right, so the piece of metal lost energy and the water gained energy. And so that's what we're going to look at. When we look at our equations, the Q of the water is going to equal the negative energy of the metal. That's because you have your law of conservation of energy. Energy cannot be created or destroyed. So therefore, if one of your substances is losing heat or losing energy, then that means that something else must have taken in that energy that it was losing. So the heat lost is equal to the heat gained. Let's look at some examples with that. So 125 grams of water at 25.6 degrees Celsius is placed in a foam calorimeter. And then I have a 50-gram sample of an unknown metal heated to a temperature of 115 degrees Celsius. I'll place that hot piece of metal into my water, and as a result, they both finally reach an equal temperature of 29.3 degrees Celsius. Using this information, we're going to determine the specific heat of the metal. So one great way that I really like to go about these calorimetry problems is with this table. All right, so you're going to look at the variables that you have and solve for what you need. So if I'm looking here, I have QW, which stands for the energy of the water. All right, so this whole left side is going to be for water, and this whole right side, QM, is going to be for metal. All right, you're going to use this table to walk you through finding what it's asking for. So let's plug in the information that we're given. Up here, I'm given that I have 125 grams of water, so I'm going to put that under my mass side of water, 125. And then I know that that water is at a initial, so what I'm going to be subtracting, initial temperature of 25.6. Remember, change in temperature is final minus initial. All right. Then I'm given 50 grams of an unknown metal. So over here for my mass is 50 grams. And that metal has a initial temperature of 115 degrees Celsius. Both the water and the metal attain a final temperature of 29.3. So now I can plug that in on both sides. Determine the specific heat of the metal. So I'm looking for C over here on the right side. All right, well, in order to do that, I need to find C of water. Well, what do you know the C of water is? We referred to it a few times back, and I'll flip back so that you can see it. 4.18. So let's flip forward again, and we're going to plug that into our table. 4.18. Using those three values, I can plug them in and find my Q value, because remember, Q equals MC delta T. So I'm going to multiply my MC delta T together to get a Q value of 1,933.25. So that's how much energy the water took in and absorbed from that piece of metal in order to heat up the amount that it did. So if that's how much energy the water took in, then the metal must have lost, so negative lost, that same amount of energy, 1933.25. All right, so now that I have that information, I can go and I can solve for my C value. All right, so in order to do so, I'm going to need to plug it into the equation. Let me get some space up here at the top, and let's find our actual delta T so that we can plug it in. Taking that 29.3 final temperature and subtracting our initial of 115, I get a delta T of 85.7. So let's plug this into our equation and solve for C. Trying to find some more room here. All right, so I have a equation of Q equals MC delta T. Q value of negative 1933.25. Remember, this is negative because it's equal but negative, equal but opposite of our water, equals a mass of 50 times our specific heat, C, times our change in temperature of negative 85.7. All right, combining like terms again, simplifying this right side, I get 4,285 times C. And that is equal, again, to my Q value of negative 1933.25. All right, in order to solve for C right here, I'm going to need to divide both sides by 4,285 so that I move all of my numbers to one side, 4,285. And overall, when I divide those two numbers, I get a C value of 0.45 joules per grams Celsius equals the C value of that unknown metal. All right, so now I can go in and plug this in, and I'm going to say it's 0.45. Another example here, we're going to put 352 grams of water, so there's my mass, 352, into a calorimeter and find that its initial temperature, so what I'm going to be subtracting, is 22 degrees Celsius. What mass of 134 degrees Celsius lead, so that's my initial, can be placed in the water so that its equilibrium temperature is 26.5. So that's going to be my final temperature, 26.5. Let's go ahead and find our delta T for these two substances. Delta T of my water would be 4.5, and the delta T of my lead or my metal is going to be negative 107.5. All right. So we know we're dealing with water, and that C value of water is 4.18. Again, that's a given constant that you all will always have, and it's never going to change. Water will always be 4.18 for your specific heat. So again, to solve for Q, you've got your equation. Q equals MC delta T. So I'm going to multiply my MC and delta T together, and therefore I'm going to get a Q value of 6,621.12. If that's how much energy is absorbed, then that means that much had to be released from the other side. So negative 6621.12. All right, now I can use that information to go back and find the mass that it's asking for. So let's zoom in here so we have some space. All right, got our Q equals MC delta T. My Q value again is negative 6621.12, and that equals a mass that I'm trying to find times my C value, or my specific heat, of 0.129. Again, that's a given. They'll always give it to you unless that's what you're solving for. Got that from our reference sheet back there. Times our change in temperature of negative 107.5. All right, so simplifying, combining like terms here on the right side, and I'm going to get M times negative 13.868. All right, and that is equal to our Q value of negative 6621.12. So to solve for M, I need to divide both sides by my negative 13.868. Negative 13.868. This side cancels out, and I am left with a M value of M equals, those two divided together, it's going to give me 477.456. All right, so now I can plug this in here, and I've got the mass 477.456. Let's look at example 3, last example here. A 2.50 gram sample of zinc, so that's my metal. I need to go to the metal side of my table. I have 2.5 grams, is heated and then placed in a calorimeter containing 65 grams of water. All right. The temperature of the water increased from 20 to 22.5. So I'm going to put 22.5 as my final minus my initial of 20, which equals 2.5 change in temperature. What is the initial temperature of the zinc metal sample? So I know my final is 22.5, but I'm trying to find the initial temperature so that I can see where it started. All right, so first let's find our information from water. Again, we know the C value of water is always 4.18. Q, again, equals MC delta T. So let's multiply our MC delta T together here, and we are going to get 679.25. If that's how much is absorbed, then the metal must have released that much, 679.25. All right, we are working with zinc here. Oh, and I didn't read this part. It gives us the specific heat. Good. So we don't need to flip back and look for it. The specific heat of zinc is 0.390. So now I can go ahead and solve for my initial temperature. So because you don't see initial temperature in this equation, we're going to need to solve for the delta T so that we can then solve for our initial temperature. So let's go ahead and walk through that together here. So then our equation, Q equals MC delta T. And I'm going to try and fit this all in this corner over here. Don't have a lot of space. So Q is negative 679.25 equals my mass of 2.5 times the 0.39 in delta T. So again, combining like terms here, 2.5 times 3.9 is going to give me 0.975 times delta T equals negative 679.25. All right, solving for delta T means I'm going to divide by 0.975, divide by 0.975, and you are going to get negative 696.67 equals my delta T. All right, now that I know that's delta T, what must my initial temperature have been? So if there is a 696.67 drop in temperature to get all the way down to 22.5, then let's add those together, 696.67 plus 22.5, which will give me 719.17. If you double check yourself and subtract those, 22.5 minus 719.7, you will see that they equal negative 696.67. So always go back and double check yourself and just make sure that you didn't get your negatives and your positives flipped around there. Now we have found our initial temperature of 719.7 degrees Celsius. So our initial temperature was 719.17.